So today we're going to be starting antiderivatives. And now all an antiderivative is the exact opposite process of a derivative. Most often we write an antiderivative as capital F of x. Now this is generally when we're given the derivative f of x. We don't go around and write every antiderivative as capital F of x, just when we're asked to find the antiderivative. So let's go ahead and take a look at a few examples of finding the derivative. We should be very familiar with this at this point. So if I find the derivative, considering that this is the antiderivative, like I said, commonly we don't refer to it as this. But if I take the derivative of f of x, I'm going to say f prime is going to be, I'm going to multiply 3 times the 10 and then subtract. So I'm going to say that is going to be a 30x squared. So let's go ahead and jot that down. We are multiplying and then subtract. So in the power, we multiply power times coefficient and then subtract 1 from the power. If I do the same right here, the first derivative of this is going to be, let's see, 3 times 10 is going to be 30x squared because I take away a 1. We know all constants disappear, so I'm going to cross that one out. If I look at this one right here, my derivative is going to be 30x squared, and all constants disappear. And if I look at this one, again, we're noticing a trend here, and we're going to ask a question: what happens if the constant always disappears? How are we going to go from the derivative, which in this case we're shown as f of x, how do we find the original function that it came from? If this same function, which is what we're given, can come from any single one of these. So you might ask yourself 2 questions. Well, how do I find it? And how would I do it? Well, if we look at our steps over here, we multiplied power times coefficient and then subtracted 1 from the power. So we're actually going to do that in straight reverse. What we're going to do is we're going to add 1 to the power. So I'm quite literally going to take that x squared and make that let's actually write this off to the side. I'm going to make that an x2 plus 1. I'm going to add 1 to the power. And then if I multiplied, I'm going to have to divide. What am I going to divide it by? Well, looks like if I multiply by 3 and I add 1, I'm going to be dividing by that 3. So I'm going to take that 30 and I'm going to divide it by that 2 plus 1. So what I'm left with is okay, that is x cubed. And then 30 divided by 3 is going to give me a 10. So my antiderivative is capital F of x is equal to 10x cubed. But we said it could be pi, could be -4, could be 1, could be 0. So the way that we traditionally show this is we're going to say this is what we know. The antiderivative is 10x cubed. And we're going to pop in let's do this in purple because we haven't used that color yet, plus c. So plus something, which could be plus pi, could be -4, could be plus 1, it could be plus 0. Doesn't matter what, but this is how we find the antiderivative. And we see the fact that the 2 processes are literally just reverse of each other. So what we're going to do, let's go ahead and jump off into number 1, is we are going to find the antiderivative of the function and use our T84 to sketch a graph of the primary antiderivative. Then we're going to sketch at least 2 other members of that family of functions that the antiderivative could contain. So let's get our handy dandy T84 ready, and we're going to find the antiderivative of x cubed. So let's take a look. We know that the antiderivative means that I'm going to say, okay, that's going to be x to the 3 plus 1. Actually, I'm going to write this in black because these are the parts that we don't change. So the 3 plus 1, and I know there's an understood coefficient of 1 right here. But what I'm also going to do is I'm going to divide by that 3 plus 1, which if I reduce is going to lead me to my full antiderivative, f of x is equal to let's see, that's going to be a 4, so 1/4 x to the 4. And we can see that if I were to find the derivative of this, 4 times a 4th is 1, subtract 1 is 3. Exactly. But don't forget, we're going to include our, we said that we're going to do this in purple, so let's keep that up, plus c. That is our primary antiderivative. What we're going to do is we're going to sketch a graph of that. So we're going to open up our graph and say, let's see, 1/4 x to the power of 4. And we're going to take a look at this, and boom. We know that that is just a basic 4-3 polynomial, so it's going to come up like that. So when I sketch a graph, I know the primary antiderivative looks something like this. And we want two other members of the family of functions. So that plus c, what that's going to do is that's going to take this graph, and it could be that same graph plus 1. So I could take a peek at what would that look like if I wanted to in my calculator. I don't need to do it at this point, but I could say, how about 1/4 x to the power of 4 plus 1? And take a look at the two graphs. Oh, hey, it's the same graph, just moved up 1. I could say, how about plus 3? I get my original graph and plus 3. And we notice that the original, or the moved graph can be moved up. Or what we could do is we could say, how about instead of adding, we could say, how about minus 3? And so the graph could be moved straight down. And there we go. And what you notice is that a lot of people will just span the graph out like this. You notice how the graph is much closer right here? Because the graph moving up and down, these are getting closer to vertical. So it's going to be very close to the edges right here. And the only point where you're really going to see the change is kind of where the graph is mostly flat. But again, we're not too terribly concerned with the sketches. This is just a sketch to show that all three of these graphs will produce the same derivative, all of them. So let's try number 3. We know that the antiderivative is going to be capital F of x is equal to, and we need to keep a few things. I need to keep this x to the 4th, and I need to keep this minus 1 x cubed. What we're going to do is I'm going to add 1 to the power, so plus 1, and I'm also going to divide by that 4 plus 1. So 4 plus 1 is going to be 5. I'm also going to over here divide by that 3 plus 1, which is 4. Now I'm going to go ahead and draw my coefficient right here. So I know that my primary antiderivative is capital F of x is equal to 1/5 x to the 5th minus 1/4 x to the 4th. There's my primary, and all other antiderivatives plus any number minus any number are also going to produce that same derivative. So if we draw a sketch, boom, we get that right there. What we'll notice is that this is probably going to be, I could factor out that x, it's probably going to be, let's see, positive, so it's going to end up going up with a 5th. It's probably going to come up, flatten out at the 0, and that next root is going to be a little over. So let's take a peek at what this would look like. So let's clear this. We have 1/5 x to the 5th minus 1/4 x to the 4th. And so what we notice is this almost looks like a cubic function. But if we zoom in really close right here, so let's set our window to, let's say, -3 to 3. And let's zoom in really close. Let's say -1 to 1. Let's take a look at that graph. It actually comes up, and it dips down just a little bit right there. In fact, if we zoom in even closer, -0.1 to 0.1. Oh, I think I changed the range. Oh, yeah, to 0.1. There we go. Yep. So we see the graph comes up, dips down, and then goes up. So our primary antiderivative is going to look something like this, where it flattens, dips, and then goes up. Again, this is a sketch. It's not really drawn to scale. Actually, that is drawn to scale, just a very small scale. But our plus C is we can move this graph up. Not necessarily the best up. I could move it up again. Or I could move it down. And it doesn't matter where you're moving it. You could move it up, you could move it down. All of these functions all produce the same derivative. So let's go ahead and try number 5 real quick. Pause the video, unpause it when you're done, and see how well you did. Okay, let's take a look. We know the primary antiderivative is capital F of x is going to be equal to, and I'm going to keep most of this information, 8x cubed minus 3x squared. But I am going to add 1 to the power, and then I'm going to divide by whatever that power plus 1 is. So 3 plus 1 is 4, 2 plus 1 is 3. And that's going to lead us to capital F of x is equal to 2x4 minus 3 divided by 3 is 1, so just minus x cubed, and plus c. So this is our primary antiderivative. And if we draw a sketch of what's going on, let's take a look. I'm going to pop this in there. And we have 2x to the power of 4 minus x to the power of 3. So that's a positive even, so it's going to be both going up. Factor out 3 of those as 0. So I should see a flat line, maybe a dip down. Yeah, because I have 3 of them, so it's going to be a cubic through the 0 and then back up. Oh, actually our scale was perfect. Our zoomed in scale. So yeah, it's going to be flat through the 0 and then curve back up. So it's going to come down, flatten out, curve down, and then pop right back up. And again, there's our primary antiderivative. We can shift this down. We can shift this further down if we want. Or we can shift this up. Any one of these works. Awesome. So let's go ahead and take a look at the last one, number 7. So this one's a trig function, so why don't you go ahead and pause the video, give this one a shot, and see if you can figure out how to find the antiderivative of a trig function. This isn't normally a power, but see if we can't get this one. Okay, so what you might have noticed is the fact that we don't have any unique trig function which produces the sine of x. However, we do know that if we take f of x and set it equal to the cosine of x, the derivative f prime of x is equal to the negative sine of x. And that's really close. Yeah. So that's going to be a really close thing. So if that was only a negative sine of x, we could very easily make that work. So why don't we just go ahead and say, well, if I need that to be a negative sine of x, how about I pull out a negative to make that a negative? Let's take a look at how that would look. F of x is equal to a negative sine of x. So now do I have something right here that matches? Yes, I have the negative sine of x right there, which is going to tell me that my antiderivative, capital F of x, is going to be equal to, I'm going to keep that negative on the outside and just pop it right there. And I'm going to say the antiderivative of this would be the cosine of x. And so again, if I looked at this, the negative cosine of x, well, that would just mean move the negative out, make it a negative sign. Negative sign would be positive sign. This does work. And let's not forget, that we're going to add any number. So how well did you do on that one? In this case, I have just pull out a negative, make it look like one of those derivative rules that we can reverse. Most of trig is just going ahead and trying to set the expressions equal to something where I say, hey, I can produce that, this I can reverse. We know with this one, we don't really need to graph this. If you wanted to, we could. It's going to look like a negative cosine function, which is just like this. Maybe not that skinny right there, but we get the point. So if I had a negative cosine of x, and I make sure that my mode is in radians, the window, I'm going to make this a standard window. There we go. Actually, let's zoom in a little bit. Yep, so we see our cosine wave right there. So any sort of cofunction whoop, 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 would be up or down. Any one of those functions is going to produce the same derivative. So how would you do on that? Now, all of that is going to bring us to our next set of problems. Now, these aren't so much concerned with the graph. These are more concerned with finding the antiderivative and introducing this new thing called integration. And we're going to see integral notation introduced here and how we're going to use that going forward. So let's take a look. Differentiation is considered taking the antiderivative or taking that primary function and finding the derivative. So I would say, okay, big F of x plus c is going to be 5x cubed plus 2. And if I find the derivative of that, 5 times 3 is 15. To take away a power, get rid of the constant, boom, we have that, which is going to be the way that we are going to write integral notation. Integral notation is written in the language of the derivative of that. So integration is reversing it. How do I go from here to here? Well, I'm going to write this thing. I'm going to say, hey, if I take this and work it backwards, the integration of this function is that. And now this is an indefinite integral. Doesn't have a start and a finish, so we're going to say, boom, there we go. So let's put that into practice. So we've got several problems right here, and we see the fact that the derivative and the integral notation are exactly the same. The only thing with the integral is I do have the dx on the outside and the integral symbol, which looks like an elongated S. It's kind of like how most of us draw our F's if we don't still draw the comical f of x. A lot of us draw our f like that of x, which kind of looks like an integral. The antiderivative is when we take the antiderivative, obviously, of the derivative. So let's go ahead and get started. So the first and easiest part would be what I would do is I would go ahead and take the derivative of these things. And then once I found all the derivatives, I would say, boom, I have that, boom, I have this. And then I would take the derivatives and find the antiderivatives, and that would be the worksheet. But let's go ahead and start this in tried and true form. Let's start with number 1. So if I have this derivative, I know my antiderivative is going to be the equivalent of, let's go ahead and grab a sheet of paper. So what we've got here is I know that I'm going to keep the 30x plus 1. So 30x plus 1. And what I'm going to do is I'm going to say, well, that was a 1. So actually, let me draw this up here. So there was a 1 on the x. I'm going to add a 1 and divide it by that 1 plus 1, which is 2. Now, what you don't see right here is that that constant actually does have an x, but that's an x to the 0th power because we don't see it. So what I'm going to do is I'm going to add a 1 and divide by that, which is 1, which is going to give me an antiderivative of, let's see, 30 divided by 2 is 15, x squared. Let's see, that's going to be plus 1, so I'm not going to write that, x. And the big thing we can't forget is that plus c. There's my antiderivative. And the next thing is if I take this and write this in integral notation, let's do this in blue. I'm going to say, okay, my integral is going to be 30x plus 1 dx. Integral notation and the derivative are in essence the same thing. Not a big deal. If you're given the antiderivative, the process is a little more straightforward. I just take the derivative and I say, okay, 3 times 13 is going to give me 39. Take away 1 from the power, so that's going to be x squared. Multiply that, so I'm going to get negative 24x. And for integral notation, again, kind of just copy it down. The integral of 39x squared minus 24x dx. There we go. Let's actually zoom in a little bit. I think it's hard to see. And then if we're given interval notation, it's the same thing as being given the derivative. I can go ahead and I can copy this down as the derivative because I know the derivative is going to be 1 over x cubed. I just need to find the antiderivative. So finding the integral, the indefinite integral, is just finding the antiderivative. So let's go ahead and let's bring back out our scratch paper. And we've got it written right here, so why not? So if we have 1 over x cubed, another way to write that out, let's see, this was number 1, this is number 5. If I have 1 over x cubed, I'm going to write that as 1x negative 3. This is going to allow me to say, okay, plus 1 divided by negative 3 plus 1 is negative 2, which is going to simplify down into, let's see, that is negative 1/2 x negative 2, which is, if I further simplify that, negative 1/2 x squared, which is really just negative 1 over 2x squared. There we go. So we have negative 1 over 2x squared. And let's not forget r plus c. So taking the integral and finding the indefinite integral is just finding the antiderivative. Okay. Number 7, if we have something like the secant squared, remember, finding the antiderivative is just finding which trig derivative rule produces a secant squared. And one of the things that we will, as I drop that, remember is that to produce a secant squared, if I take the derivative, if I have f of x is equal to the tangent of x, I know f prime of x is equal to the secant squared of x. So I know if I can go that way, I can go reverse and say, hey, my antiderivative is going to be the tangent of x plus c. Awesome. And then easily enough, my integral notation is going to be the integral of the secant squared of x dx. Okay. Same thing right here. If I take this and say, okay, my integral, I know that is going to be my derivative, is 2 sine x. Go ahead and take a moment, pause, try and figure out what the antiderivative would be of this expression. Okay, so if you remember that trick that we did earlier, we know that on number 9, we have, okay, I know that the derivative, so if I have f of x is equal to the cosine of x, I know f prime of x is equal to the negative sine of x. So I need to make that into a negative sign. So all I'm going to do is I'm going to say, hey, how about let's make 2 sine x into negative 2 times the negative sine of x. Because that, when I multiply that together, will give me 2 sine x. But it does allow me to take this and revert it backwards. So I'll have negative 2 cos of x. Actually, it's negative 2 cosine of x. And a lot of people say cos. It's one of those things that I always try and fix whenever I encounter it. Okay? So now we only have a few left, so why don't you go ahead and try some of these fun ones. That was number 9. Go ahead and try number 11, number 13, and number 15, and see how well you do. Unpause the video when you're done and check your work. Okay, so let's take a look. 11, not too bad. Pull out my green pen. For this, I know that's 1x negative 2, so I'm going to say negative 2 times the 1 is a negative 2. And that negative 2, I'm going to subtract 1 to make that a negative 3, which is x cubed. Awesome. Which means my integral notation is the integral of negative 2 over x cubed dx. 13. Kind of looks like we've recycled a problem right here. Same thing as what we had earlier. So let's glitch and say negative 2 cosine of x plus c. And for the integral notation, I'll have the integral of 2 sine x dx. Kind of a cheap thrill there. But number 15, 15 is the fun one. So for number 15, what we're looking at is to find the derivative of this isn't too big of a deal. Well, to find the derivative of this, we just copy this down. So x plus 1 over the root of x. But finding the antiderivative, this isn't a standard, okay, this looks like I have a quotient. Well, how would I turn this into something that looks like either a simple trig function or maybe something with a set of powers, but I have powers on top and powers on bottom? How would I work that? Well, let's go ahead and copy this down real quick. 15, x plus 1 over root x. Let's see if we can't turn this more into a polynomial form. Okay. Well, the first thing I would do is I would split this up. I'd say, okay, how about I split the numerator into 2 parts? So that'd be an x over root x plus 1 over root x. I notice that right here, that can probably reduce, and this can reduce a lot. I can just say, hey, I know what the right side is. That's going to be plus 1 over x to the, well, if that's 1/2, negative 1/2. And that will be pretty easy to find the antiderivative of. This part, I know that's going to be x to the first, and that's x to the 1/2, which leaves me with an x to the 1/2. At this stage, that's where I go into find the antiderivative. X to the 1/2 plus 1, x to the negative 1/2. We add our 1, and we divide by whatever that sum is. So 1/2 plus 1 is 3/2. Negative 1/2 plus 1 is 1/2. So if I take this, 1/2 plus 1 is 3/2, and if I divide by a fraction, we're going to keep change flip. So that's going to be 2/3 x to the 3/2. Again, if we divide by a fraction, keep change flip. That's going to be 2 over 1. 1/2 plus 1 is 1/2. Then at this point, we just rewrite it in a form that looks more like standard notation. So I'm going to rewrite this in radical form. I have 2 choices. I could either leave the x cubed beneath the radical, or I could factor out one of those. Because I know 3/2, let's do this in blue. 3/2 is equal to 1 plus 1/2. So I know 1 full x is going to be outside of the radical, but I will have a square root of x left in there. So this is going to be a 2x for my full x that comes out, and the x to the 1/2 is going to be root x all over 3. I could put it all over 3, but I'm just going to put the 2/3 out front. Here I'm going to say plus 2 root x, and that is my antiderivative. Let's copy that down. down onto our sheet right here. Oh, I'm a little too close. So it's going to be a 2/3 x root x plus 2 root x. If you wanted to combine that all back into 1, you could, but I think that's good enough. Theoretically, if I wanted to, I would just have to divide that by times by 3/3, which would be a 2/3 x root x plus 6/3 root x, which would be a 2x root x plus 6 root x all over 3. If you wanted to do that, I don't really see a reason why we would want to combine it into 1, because I think that's simple enough. And there you go.